and to record it. Let me remind you that the purpose of this class is to check how you guys doing. It's like office hours, as Andrew explained, to check how you're doing on the homework, see if there are any questions, issues, fix them up, maybe solve similar problems to, reinforce your skills on that particular topic. And by next time, before next class, by like Sunday night, you need to submit the final version of your solution. So Vincent, since you have the priority on everything, do you have any questions about this homework? Did you find anything worth of discussion?
Let me see. I mean, I had a lot of trouble with most questions.
But you did fine in most of them.
above an 80 in terms of percentage, like above 80%.
I'm pretty sure. I didn't count, but yeah, it looks like yeah.
I mean, I didn't know how to do number 6, I don't think, because I didn't know how to use the actual equation. So I didn't know how to do that.
Okay. Anything else?
Let's see. Number 7, I wasn't sure about the acceleration. I guess it was the reciprocal of A. That's for 7. As for, I'm pretty sure I knew how to do 8. For 9. Yeah, 8 took the most time, I would say, because I had to graph everything and check everything. As for 9.
Okay, let me check. So 8.
Four was also pretty hard in terms of I had to check everything on the Desmos.
So actually 7 was meant to be easy. Yeah, we kind of started it last time.
I meant 8.
8, yeah, let me check that. Yeah, I mean, it's close. Yeah, it's all good, yeah. And 7, you want to double check it.
All right, I'll check 7 again.
Looks like you're on the right track, but you want to double check it. And yeah, double check 9. Okay, I'll maybe using a different reference frame. In number 9, when you say the total displacement of the block, is that with respect to the slab or with respect to the table?
I'm pretty sure it was the table.
Okay, then I would ask you to double check that as well.
Okay.
So, yeah, so folks, let's, hi, Andrew. So let's do this. So when you submit your draft of the homework, do you also see that comment box where you can type your comments or questions? or is it just
Yeah,
me?
there's a private comment thing.
Awesome. Okay. So why don't you just highlight if you have any issues with a specific question or comment, then I'll just look into that more carefully.
Yeah, I just had like a late start to this homework. So yeah, my apologies if it comes in later.
Well, the hard deadline is Sunday. So the point of this meeting, as I mentioned, upon your request,
Yep.
is for you to check where you are, and if you have any issues, we could fix them so that you know what to do and how to finish by the actual deadline. Because yeah, if nobody submits anything, there is really no point doing the meeting. Okay, so I see 6 people, and that's the same 6 people who got to the Google Classroom. Andrew, perhaps you know better. Is anybody else planning to be with us regularly?
So I don't know where Derek and what was this thing? Was it Gavin and Josephine? Were those the other 2 that were here, Alvin?
It was Brian and Josephine.
Brian and Josephine.
Yeah, Josephine hasn't responded to your question in the thing, so.
And she's online right now,
Uh-huh.
which is confusing me. I mean, hopefully we should have Brian and Josephine back here too. I kind of don't know where they've disappeared off to. There should also be one other person that I can actually message right now because Ahmed, he should have been here.
Okay.
We might be adding in like 1 or 2 new members. Just we'll do that like maybe closer to the beginning than the middle, but yeah, I don't know.
Okay. Well, yeah, just make sure they can catch up on what they missed. Okay. So we're discussing Vincent's submission because he submitted every problem and he has some questions about some problems. So that's what we'll start with.
So do I just talk about some problems I had trouble with?
So you mentioned 6.
I think I had trouble with like 5, 6, 7, and 9.
5 you did right, but we can still talk about it, no problem.
I just didn't know if there was a faster solution because I did it a really long way.
5? Maybe just slightly faster, but yeah. So I expected first one to be a challenge, but it looks like you did it okay. So just to check, everybody was here last time, right? When we discussed the bounce of a ball, of a moving wall, right? There is this unexpected outcome that the ball gets twice the amount of speed of the wall on top of its own speed. So with that in mind, number 1 should be like fairly straightforward. Okay, so I'm seeing your questions. I'll start with Vincent's because, you know, as the person who submitted most of the problem has the priority. So do you want to start with number 5?
Sure, why not?
Okay, do you mind if I just pull up your work and comment on it?
Yeah, that's fine.
Okay, sure. Let's do that. Yeah, so this is number 5. So I would actually start with a graph. And then you see that you can actually, this is my strong recommendations. In problems like this, do the graph first. And that will just tell you what exactly you need to compute, because a lot of things you either won't need to compute as like irrelevant, or a lot of things would just be obvious from the graph itself. Recordings are posted in the stream or somewhere. I'll show you, after we finish this problem, I'll show you where recordings are posted. Okay, so this is pretty much the graph you need. I would not just call it X. First off, it's not an X, it's a time. And second, you want to use a different variable for different things, okay? Because your X in this graph is not the same as X in this graph. Other than that, this is the way to go. So let me just.
I mean, I had a hard time finding out the relationship between like T1, T2, and T3. That's why I did that first, and then I did the graph, because I didn't know it was going to be separated into a ratio of 2 to 1 to 2 before.
Okay, just give me a second. Oh, so there are just T1 and T2, okay?
Yeah, I'm talking about the top.
Yeah, so well, maybe I'll just draw it someplace else. So, or maybe I'll just draw on your graph. So first off, you know that in the first situation, the areas are equal, right? The displacements are equal, so that means the areas of the velocity versus time graph are equal.
Okay.
So the height is the height is the same for all three shapes, but the middle one is a rectangle, which would normally have twice as much an area if there was the same base. But if you want the same area, this base, the middle base, needs to be 1/2 of each of these bases, right? So if you want to split this whole interval in this ratio, right? This is like what, 2.5. So it takes a little bit of arithmetic to figure out that if you call this whole time period T1 for the whole trip, then this needs to be 0.4 T1. This is also 0.4 T1, and this is 0.2 T1. Right? They form the right ratios, and they add to T1. Then in the second graph, it's even easier because the times are equal. As you pointed out, right? You call them all X, but I would call them 1/3 of T2, 1/3 of T2, and 1/3 of T2. Okay, and then you just need to write two equations for the two unknowns, T1 and T2, right? So two equations. One equation is the equality of the areas because they cover the same trip. So total area here must be equal to total area here. Yeah. And I'm not going to write it explicitly. Every one of you can do it, right? So total area 1 equals total area 2. That's the first equation. And the second equation is just the given fact that 1t is 2 minutes longer than the other. Right? The 2-minute difference. So, so by working out these two equations, you get all you need. Make sense? So I guess you spent the top of your work figuring out these ratios, but so that's good. But
yeah, I didn't realize that I should have drew the graph and then realize that it's a triangle and a rectangle, and then
Yeah, that's what I'm saying. That's what I'm saying, because you know something that helps you save some steps. How's everybody feeling about this problem? You good, guys? Have any questions?
Makes a lot more sense.
Okay, great. Okay, so the next one was number 6 or number 7.
yeah, number 6.
Okay, so again, let me give you some hints. Again, start with a graph. So it is a parabola. Right? Am I talking about? That's where you were given trajectory, right?
Yeah, I think the original equation was like y is equal to 0.04 x squared.
Yeah, so let's just say y equals some constant x squared. And the particle starts at the origin. At the origin, the tangent is horizontal, so you know the particle has purely x velocity, which is also given, right? And you need to find, yeah, perhaps. Oh, 2 seconds later, okay. Yeah, so let me put it all here. Given, you know the A, it's a specific number, you know V naught. You want to find V at t equal to 2 seconds. And there is one more important piece of knowledge here. What is it?
Well, you're not given anything else, but you can find like the force.
They actually tell you that the force is constant, right? They
Yeah.
don't tell you what it is, but they tell you it's constant, so it's an important piece of information for us. Yes, V is equal 10 meters per second initially. I'm not putting that number explicitly, I'm just listing that as it's given. So, and again, so the point of today's class is not to solve the problem for you, because that will defeat the purpose. It is to give a hint if necessary, or just maybe clarify something that's unclear. So first off, constant force, you immediately understand that it implies a constant acceleration, right? And that's really all we need from this piece of knowledge, that it's a motion with constant acceleration in 2D, and the trajectory is a parabola. So, but in essence, it's kind of projectile motion, maybe upside down, right? So in general, if you just know the trajectory and some initial data, you can't really tell much, right? You don't know what's gonna go, like what's gonna be happening with this particle later on. Trajectory is basically like a track for a train, the shape of the track, but it doesn't tell you about the dynamics. Okay.
Can you use the general equation for parabolic motion and just
Exactly. Well,
for A?
again, not parabolic. I would even like say projectile, maybe with upside down acceleration. But so this is an important piece of information that tells you that the acceleration is constant, right? So that immediately tells you which direction the acceleration is pointing, right? What is it? Yep, it must point straight up. Okay. And then, yes, Alvin, go ahead, use all the equations you normally use for projectile motion, just upside down projectile motion, and that should do the trick. Okay? So you might want to like use the trajectory equation for projectile motion. Is everybody familiar with that? Trajectory equation. This is an equation that expresses y versus x without any time. It says delta y equals delta x times tan theta minus g delta x squared over 2 v naught squared cos squared theta. Does that ring a bell, folks? So this is it. This is it. You basically given this parabola that, you know, the initial angle is 0, that helps. So this whole term drops out, right? And cosine is just 1 then. Up to this minus sign, this is it, right? So you'll figure it out, okay? Of course, in addition to this equation, you can use the standard equations of motion that contain time. You'll need those because, of course, you're given a time, so you'll need to plug it in somewhere. So do you folks think you're good here? Think you can finish? Yeah, okay. Great. Oops. I'm saving it. Okay, Vincent, what's next?
The next one is 7.
Okay. Yeah, this one was meant to be easy. Let me ask, has anybody figured it out? What's the main like idea that allows you to simplify everything dramatically? Leon, yes, this is it. Folks, does this make sense to you? So this is a motion with constant acceleration in disguise. Just think about it. For motion with constant acceleration, what do you have? You have this v squared formula. The final squared minus the initial squared equals 2a delta x. Just compare and contrast these two equations. You'll recognize it's the same equation. Just identify the constants here with the constants in the given problem. And then again, use whatever other equations you know about. This is one-dimensional motion with constant acceleration. Okay. So Vincent, I'm not exactly sure what went wrong. It looks like you probably made a mistake in the acceleration. So the answer is not quite this. You're off by a factor, simple factor. But yeah, just double check your acceleration value, and that should do the trick. So it looks like you did recognize that this was motion with constant acceleration. Yeah, this is the main thing. If you don't recognize that, this problem is pretty hard. But once you figure that out, it's not that difficult. Folks, any questions about this problem? Yeah, so this is it. This is a typical Olympiad trick to disguise some simple motion that you know very well, but you may know it in some representation. They love to disguise it into some tricky looking thing. For example, you know how to write x of t and v of t for constant acceleration, but they kind of disguise it x versus v or v versus x, or last time you also saw x versus a or a versus x. Okay, so you may want to just familiarize yourself with all these variations, so when you see them you actually recognize what's going on. Okay, so Vincent, what's next?
Number 9.
Number 9. Yeah, number 9 is again not meant to be difficult. Just need to carefully do the bookkeeping and be careful with your reference frames. Okay, so let me bring that up. And actually, let me answer Joseph's question. So if you go to the group, go to classwork, and hit this, you'll see the 2 links to the 2 classes. These are the video recordings of this class. Does that make sense? Okay, so and as time goes on, I'll post more stuff in here. And this is the homework. So this is the problem set. Yeah, so this is number 9. So the thing is, so this acceleration is with respect to the table, I believe. But again, some of you may want to switch to the slabs reference frame. And then just be careful because that frame is not inertial. It's accelerating. And as such, you will have to account for forces of inertia. So this is not the way to go for now because we kind of officially we're not discussing forces of inertia yet. So we're doing kinematics. So I just try to do it from the laboratory frame perspective. Okay. So this problem was not meant to be difficult. Vincent, maybe you have a specific question?
I think I was just really messy with my writing, I think, maybe.
Okay. Yeah, just give it another try and do let me know if you have any questions. Actually, let's do an experiment. Why don't you put a comment or Andrew, wherever you said there is a comment box for you folks, because I want to check if I'm receiving any emails about it or if I need to actually check myself to see if anybody made a comment.
It should be both. You should both see the comment and get an email that somebody added a private comment.
So that would be great. That way, whenever you ask me a question, I would see it and could respond without actually checking things.
I just posted a private comment on mine. You should be getting an email.
Let me, would it show up somewhere here?
Well, here you'll have to check, but in your email, there should be an email that I added a private comment on this assignment.
Yeah, I just got it like a minute ago. Okay.
Cool.
So that works. So folks, yeah, this is the way to go. So if you have additional questions, even after you submitted your work, do use that and I'll get your question. Okay. So Vincent, do you feel we covered all your questions now?
Yeah, I think so. Unless I missed another question. I think those are the ones that I missed.
Yeah, so 7, I told you, just double check the acceleration. All the other Problems look good to me. So that's good. Everybody take after Vincent. Let him be your role model.
It was my bad for sending out the link so late, so that's on me. I'm sorry.
You know what else is on you? The emails. And well, the emails are not as critical anymore as long as people join, but the tests.
Right. Okay. So I think I announced this during the Einstein meet, right? Did everybody get the memo? Because if I announced it at the wrong meeting, then that's my mistake. So like Vincent, Abjit, Joseph, Leon, you all got the message about the practice 2019 F equals MA, right? Like, yeah? No?
I haven't been getting emails.
Okay, well, do the practice 2019 F equals MA A? Did we decide on A or B? A. Just like 75 minutes, test conditions, calculator allowed, and just do it. I will make a form, a submission form where you just put in, do you want just the answers or should I have like should they like upload also their work?
Not the work. Remember, this is like a diagnostic thing.
Okay.
And then if I have some questions, I guess I could ask those.
Okay, so actually I can make the form right now. That should take no time at all.
Yeah, actually, it would be helpful to discuss it today, but
Yeah. So I think we'll be ready with that. If everybody does everybody have like 75 minutes they can take like tomorrow to do this practice? Like, I guess thumbs up in the chat if yes. Oh, you have a school test tomorrow. Okay, so anytime between Friday, Saturday, and Sunday, if you have like Saturday. Okay. So, oh, SAT. Okay, so you have the SAT on October 3rd. So you'd be able to do it on like Sunday, right?
Yeah, Sunday's fine.
Okay. So if everybody can like do it on Sunday, just take 75 minutes on Sunday to do the practice, then that will be awesome. Again, it's my mistake if I like did not make it clear here. Yeah. Alvin, I forget, is a protractor, ruler, compass, are all those allowed?
Yeah, I think you get everything, like up to a calculator.
You're allowed a calculator too. That's as long as it's not QWERTY, right? Yeah.
a scientific calculator.
Yeah, scientific.
Mhm.
I think as long as it's not QWERTY. Let me see. Calculator F equals MA. Okay, a handheld calculator may be used. Memory must be cleared. You may only use the basic functions found on a simple scientific calculator. Yep. Okay. So no integrals. Sorry, guys.
Okay. Okay. Any Does anybody have any questions about any other problems on this homework set?
I just had a question, like a conceptual question regarding question 9. Like, what are the benefits to shifting to the reference frame of the block if we know that it's not inertial? Doesn't it make more sense to just work with the friction force and just add that to our diagram? Are there like actual merits?
For now, I would say stick with inertial laboratory frame, but in some problems, I mean, there are problems where moving to this non-inertial frame is actually beneficial, but you need to account for forces of inertia. So the reason I'm hesitant to give you any specific examples right now is because I want to go logically from topic to topic. So once we get to forces, we'll start considering those problems.
Mm-hmm.
Okay, so this is really in the domain of dynamics, not kinematics.
Got it.
Well, I can give you a problem. Since most of you know forces, you could try solving it regular methods, but then we can discuss how that can be solved using non-inertial frame. So okay. Like in the simplest version of this problem, let's say this is frictionless. The table is frictionless. And the block and the slab have some non-zero friction, which is given. And let's say the masses are given. Find the minimum amount of force that should be applied to the block horizontally so as to make it slide across the slab. So you apply a force somewhere to the block. So I want to find the minimum amount of force to make it slide across the slab. So you understand, if you apply a relatively weak force, because there is no friction here, they would just move together, right? But if you apply a very large force, obviously this would slide easily. So you need to find the minimum force that would make it slide. To make M1 slide across M2. So this is one of the examples where you can actually consider the frame associated with the slab, but again, keeping in mind that it's not inertial. Okay. And you folks remember, you can say whatever I'm writing on the whiteboard or elsewhere at any time. I'm saving it and then I'll post the notes, but you can also save it if you need it for future, okay? Okay, it looks like everybody is good on this homework, so I expect you to finish and submit by Sunday night. So let's talk about some other interesting problems here. So something real tricky. And I'm going to pose the problem. I'm not sure if if you'll be able to solve it in real time, or if you need more time. So you just let me know. So as you know, right now, swimming pools are closed. So consider a circular swimming pool. Actually, you won't really need the radius, but it's fine. So a student disobeyed his teacher and jumped in a swimming pool. So here's the student, and this is circular swimming pool. Okay, so the teacher found out and now is at the border of the swimming pool. So this is teacher, student. So the student wants to escape the swimming pool and right away to avoid punishment. The teacher, of course, wants the opposite. What's given is that the running speed of the teacher can run any direction with a constant velocity of, let's say, the teacher equals 4 times the speed of the student while in the pool. So assume that if the student manages to hit the border, then he runs faster than the teacher. But when he is swimming, his velocity is 4 times smaller than that of the teacher. Does that make sense? Okay. I'm not telling you where the student is originally in the pool. You need to like think and find out, you know, like consider the general setup. So with this given question, is there a smart strategy for student to escape from the pool and not be caught by teacher? Smart escape strategy student. Okay. I'm not sure. Vincent, do you know this problem?
Yeah, I think I went to a meeting and they had this problem, I think. But it was like the swan was in the center of these or a lake. That's a circular lake. There was a bird chasing it, chasing the swan with the speed that's 4 times as fast as the swan swims.
So the same data.
Yeah.
Huh, then that's probably the same problem. So this problem has a second part, but I'll postpone that. Interesting. So I gave this problem to the camp, Olympic camp students in 2015 and 2016. Trying to remember if Kevin solved it. He probably did. We called the student Charles after one of the students, one of the campers. He actually came to both camps. Well, Andrew, that's exactly what I'm not telling you. I want you to think about this problem. So to answer this question, you don't really need to know any advanced math. There is a follow-up question, which at first seems to require advanced math. And when I say advanced, what I mean is variational calculus. Does anybody know what that is?
Variational calculus?
Yep, calculus of variations.
It's familiar. I don't know what that studies.
Okay, I can give you examples that can be solved by variational. It is related, yes, exactly. Basically, Lagrangian mechanics is based on variational calculus. But basically, when you use regular derivatives, you can use the regular derivatives to find a minimum or maximum or of a function, right? Find the number or numbers that minimize or maximize the function. Variational calculus does that for functions, trajectories, yes. Optimization of functionals. Everybody knows what a functional is? It's a map that takes a function or trajectory or curve, whatever, and gives it a number. Okay, so in physics, you know, least action principle, at least you heard the words, right? Least action principle. So you write something inside an integral, action is that functional that you want to minimize. And you need to find the best trajectory, the trajectory that minimizes it. So it's like level up compared to regular derivative calculus. Okay. So the follow-up question here, I'm going to pose it and then we can discuss some other time, because there is a smart way to circumvent all the variational calculus for this specific problem just by some coincidence, I guess. I don't know. So obviously, if the teacher runs very fast, let's say if his speed is 10 times the swimming speed of the student, then there is no strategy for the student to escape whatsoever, right? No matter what the student does, however, like he wiggles or whatever, teacher is so fast, he will always be able to meet him whenever he tries to escape from the pool, right? And here comes the question, what is the minimum speed ratio, the borderline, right? Such that if teacher's speed is less than that, student has a strategy to escape. And if the teacher is faster than that, student doesn't have a strategy to escape. So that seems to require variational calculus, but it actually doesn't. No, Andrew. That's cheating.
Dang it.
Yeah, so Vincent, if you know this problem, then you might want to think about this one, the letter one. So
I think I've also heard of this.
oh, you also know that one?
Yeah, and I don't know about like the minimum multiplier, but I think I know the method for getting away with 4.
Okay, yeah, well, disclaimer, spoiler. Yes, with this ratio, there is a strategy for the student to escape. Okay, so the minimum ratio is greater than 4. So minimum speed ratio such that there is no escape strategy. So that answer is actually a transcendental number. Elvin.
All right, let's guess all the numbers. Pi, there's E. Well, not E.
Well, it could be like e plus 1 or pi plus root 2, right? They also transcendental.
And finding that ratio does not require calculus and variations.
It doesn't, but it does require writing something that looks like a functional. The thing is that it's just a very special case that allows you to minimize it without doing variations.
Mm.
So Elvin, I'm not sure if I'm getting your question.
Right, so like, is the strategy determined on the edge of the circle? Because like, I want to say I've heard of it, but I'm not sure if I have. And
No, so for student needs to get to the edge at a place where the teacher isn't.
no, I know. I'm saying like where the strategy happens.
inside the swimming pool.
Yeah, but like, is the main part of it like where the student does something weird on the edge and then the teacher can't catch that, or am I not
Not really. Not really.
or does it more depend on the motion of the student inside, like near the middle?
Yeah. Inside the pool. Yeah.
All right.
Again, this problem. So here is the funny story, folks. So I gave this problem, in 2015, right, to the campers, and quite a few of them figured out the strategy. And once you figure out the strategy, the math is really very quick to find the um,
Optimal or
no,
minimal speed ratio.
no, I probably shouldn't say anymore without disclosing anything. So yes, Vincent. Vincent knows what I'm trying to say, but let me pause here. So, and then I gave the same problem. So I went to conference like a few days later. I went to conference on quantum gravity and gave it to grad students and postdocs. People with PhDs in quantum gravity who had a pretty solid math background. None of them could figure it out within like the couple hours that we were at that meeting. And the next day, one of them referred that he sent that problem to another postdoc somewhere else, and in the morning, and at the end of the day, he said, "Oh, I still don't know how to do it. Thank you for ruining my day." So it's not, this problem is really not about math background. This problem is about physics intuition. Okay.
I just
So
have a clarification. Oh, sorry.
Yeah, go
I
ahead.
just had a clarification question. So can we assume that the teacher and the student are always moving, or like can they stop?
They can stop. It just doesn't make sense to stop.
Okay. And also, if they move, they
Teacher may turn
immediately move.
around. Teacher may turn around and assume that happens instantly. Teacher always runs with the speed, but he may run clockwise or counterclockwise.
And the student always swims with that speed. He doesn't have to accelerate to that speed.
Again, it doesn't make sense for a student to swim any slower, right?
Fair enough.
It doesn't
Fair
help.
enough.
So,
Okay.
yeah, teacher, of course, runs most optimally. Think of this as a game theory question.
Oh my God.
So, again, teacher is a very simple system here. There are two options, clockwise or counterclockwise. Student, of course, has much more freedom, but he's slower. That's a good guess, Vincent, but
That's also what I got. Isn't that right?
this is the simplistic approach, but the actual answer is harder than that.
Oh.
It has to do with, let's put it this way, inverse trig function of some number. So it's greater than that, I believe. So there is a simple strategy. This is what I want you to figure out, the simple strategy. And for that simple strategy, pi plus 1 is the answer to the second question.
Oh, there's a harder strategy.
There is yes, there is even a smarter strategy for the student, for which the teacher has to run even faster than pi plus 1 times student speed. Okay, so again, have this problem on your background somewhere. Let me give you one more and then we'll pause and then I'll resume. So another chase problem. I suspect that Vincent or somebody else may know this as well, but let me try still. The way I know this problem is as a fox and rabbit problem. So fox chasing a rabbit. And there are different modifications of this problem. I'll start with the simpler one. So imagine a rabbit running down the road with a constant velocity v. And there is a fox hiding in the bushes somewhere on the side of the road. So the fox is waiting, and once the rabbit passes the nearest point to the fox starts running at the rabbit, always in the direction of the rabbit. Let's say this original distance is d, the distance from the fox to the rabbit. Andrew, you've seen this one? Okay. Then I'll challenge you with some other problem of this type. So what's given in this modification of the problem is that the absolute value of the fox's speed is the same as that of the rabbit's speed. So let's just, okay, put a thumb up if you know this problem. Just Andrew? Okay, good. So Vincent, you haven't seen it.
No, I haven't seen this one.
Okay, you'll have fun. So the rabbit passes the fox, and the fox starts running. So the first moment, the fox is running straight up. But then, of course, as the rabbit passes this point, the fox starts turning. Okay? So let's imagine. The first question here is pretty easy to answer. What's going to happen? What will you see happening after a sufficiently long time?
The direction of the fox's movement asymptotes towards the road.
Yes. So after a long time, you can assume that the fox is actually also on the road. So here is the rabbit. Please excuse me, I won't draw it again. So this is rabbit, this is fox. The rabbit is running at velocity v, the fox is running at same velocity v really. So that means the fox will never catch the rabbit. So they'll just keep running one after the other at a constant distance. Let's call it d final. So the question is to find this d final. Again, some of you who know how to solve differential equations may as well do it. I don't encourage you. In fact, you can solve this problem without using any calculus whatsoever. Andrew, do you also know the solution?
The non-calculus one?
Non-calculus one.
No, I only know the differential equation one.
Oh, here we go. Nice, nice. So that's a good exercise for you. Okay. Let's pause here, like for I don't know, 10 minutes, and then we'll continue. I'll challenge you some more. And if you come up with some suggestions over these 10 minutes, that would be great. If not, that's fine too. Problems of this type. Oh, thanks. And then I'll give you some other problems on the same idea. So fox and rabbit. General idea. So let's consider some intermediate situation where the rabbit is here and the fox is here. So we know the rabbit is running this way and the fox is running this way. So here is the thing. The main trick is to choose a special coordinate frame. Let's say this is the x-axis. This is not unusual, but let's call this z-axis. This diagonal axis that constantly rotates, but instantaneously it coincides with the direction of fox's velocity. Well, then let's call this angle theta. Okay, also constantly changes. In fact, theta ranges from, well, should probably not put it this way. Theta ranges or changes from 90 degrees initially to 0 degrees at the end. Okay, so what I want to do is introduce two distances. So first, distance number 1, the actual distance between the two, and distance number 2 is the x distance, the x separation between fox and rabbit. So this I'm going to call capital X, and this I'm going to call capital Z. Okay? And I want to see how they change over time, the rate of change of X and rate of change of Z. Okay? I can put it as a derivative, but I really can just put delta X over delta T and pretend I don't really use calculus, which I really don't need. Okay? But since you know calculus, it's probably more comfortable for you to write derivatives. So let's understand what's happening. Rabbit runs to increase the X. Fox runs to decrease the X, right? So we have plus V, but minus the X component of U, right? So which is minus U cosine theta. Does that make sense? Now, similarly, I want to write dz dt. So again, the fox runs to decrease z, the rabbit runs to increase z. But now they kind of swap because v goes with the cos. So plus v cos theta minus u, yeah, minus u. Okay? Let's call it equation 1. Let's call it equation 2. So what do we know now? We know that u equals v. So that means in these two equations, this is u, or everything is v. Okay? That means, do you see anything interesting yet?
Are there negatives of each other?
Exactly. So if we are to add these two equations, what do we get? We get d dt of x plus z equal
0.
Yep. What does it tell us?
It means x plus z stays the same.
Yeah, so this is a very tricky, are you familiar with the term integral of motion? If not, we'll just call it constant of motion. That means this is a tricky combo that, like, not very intuitive to consider, in the first place, but it turns out that this is actually constant. How does it help, folks? What does it?
Then because we know that x starts off at 0 and z starts off at d, then their sum just stays the same, so it's just d.
Okay. Almost there. What else do we know?
And we know that xf, I mean, we know that xf equals to zf.
Does that make sense to everybody? Because when we're dealing with finals, theta is 0 and the two x's are just coinciding. Okay. So at the end, theta is 0, x is equal to z, and equal to d over 2. So Vincent, your answer was close numerically. So it was like 0.57, but the actual answer is simpler. It's just 1/2. So what do you think, folks? Andrew,
Yep.
do you like this method?
This method is much cleaner than the calculus one. I expected this one to be much less clean than the calculus one, but this is nicer.
Calculus is fairly clean, as just or differential equation one. We can discuss it some other time.
Mm-hmm.
You know, yeah, folks, remind me your math background. So I just don't want to jump too far ahead. So how many of you are familiar with differential equations?
Yeah.
Alvin, Joseph,
Familiar with it.
Abhijit. Well, maybe we could try. Maybe we could try. So the equations are not that hard, though. So if you have some familiarity with just general ideas about differential equations, we can do that. Okay, so okay, great question, Leon. So let me pose it as a homework question. Actually, I'm going to give you a few follow-up questions. So generalizations of this problem. So imagine that the fox starts running at the rabbit, not when it passes the closest point, but some other point. Let's say fox starts chasing the rabbit when it's a distance L before or after, consider both situations, the closest point, the perpendicular. Everything else is the same. So now it's clear that the fox has to run faster than the rabbit to catch it. Well, you have, yes, Alvin, you're right, but there is still a trick. So again, I was told that no animal should be hurt. So we'll rephrase this question. We'll talk about plane and missile. Plane is just flying straight overhead, horizontally, and missile is launched when the plane is passing it. So plane is flying with velocity v. The missile is launched with velocity u, and u is greater than v. So it will hit the plane. The question is, oh, and this is still, well, let's call it h. So v is greater than u. They're both given, okay? Both given. And h is given. Find the time for the missile to hit the plane. You know, most of people care more about animals. Okay. So let me tell you when this approach is oh, bye, Andrew. Yeah, maybe we can talk about schedule so that we maximize the present. Okay, anyhow, so let me tell you. Actually, you know what? Let me give you one more problem, which seems like illegal to us right now because we don't officially know the forces. But let me give it to you. And if you don't know what to do with it for now, just don't try it. But feel free to try it, of course. So what I'm drawing is a wedge. With friction. And there is a puck on the wedge with coefficient of friction mu, and the angle is theta such that mu equals tangent theta. This is given. You kick the puck horizontally with a given velocity. Assume that the wedge is very large. So describe what happens after a long time and find whatever seems interesting to find at the end. Okay. So let me pose this as a question. What happens after a long time? Oh, Leon, you've seen this one. Okay, if I tell you that this is identical to the Fox and Rabbit problem. So yeah, this is like very, very close to Fox and Rabbit problem. In general, this approach that we discussed, specifically the non-rectangular or non-rectilinear coordinates, is very helpful whenever dealing with friction, either regular dry friction or drag force, because those forces are anti-parallel to velocity. So that means, I mean, there is always an axis that changes direction. Although it's still fruitful to consider that an axis and do equations or projections on that axis. That's a pretty powerful problem solving tool. Am I making sense right now? So once you work this problem out, you'll probably see better what I mean right now. Okay. So, folks, any questions? If you wish, I can explain how to work this out using differential equations. We still have about half an hour left. Let me just pull something up. Yeah, there are some additional modifications, but I'll ask them later. So for now, just focus on those two questions.
For the number 2, you actually need to have differential equations, right?
No. So like I said, there is still a trick. I don't want to tell you everything right now. I want you to play with it for a few days, and then we can discuss it on Monday. Okay. Yeah, so let me go back. To this setup. Maybe it's actually easier to redraw. So using DE to solve fox and rabbit problem. So here is the rabbit, the fox, at some time t, and then you give it an extra time dt. The rabbit will be here, okay, and the fox will be here, and then the new direction is this. So let me label everything. So this distance is u times dt. This distance is v times dt. This angle is theta, and this angle is theta plus d theta. D theta is negative, but just to be consistent. And now you just start writing the relationship between all these guys. So the first one we actually already have. Remember, this is the z-axis, the new z-axis. This is x-axis. So you can write that dz dt equals, so rabbit increases it with the cos, so it's v cos theta minus u, which you can rewrite as v cos theta minus 1. Okay? And then you need to write the equation for theta. So any ideas how to do that?
Like, can you like mark angles in the triangle, maybe?
Yeah, sure. Yeah, so actually, you know what? Maybe I should like mark them slightly differently.
And also, like, shouldn't it be like theta minus d theta for the
Well,
for
d theta is negative. D theta is negative.
all right. So then, yeah, the small angle there is just negative d theta.
Yep. So this angle is negative d theta. What about it? So basically, you need to express d theta. Okay, yeah. Well, let me help you here. So look at this triangle. This, and this. Okay, look at this triangle. Let's use law of cosines. Oh, law of sines. So if we take this side divided by this sine of this angle, we get, I don't know, this side divided by sine of this angle, which is the same as sine theta. So we get sine of minus d theta over v dt equals sine of theta. Now, what is this leg? This is z minus u dt. Actually, no, I should stand corrected here. What is the easiest way to write it? Probably just z plus d.
Well, that wouldn't be z minus, because z minus udt
Yeah,
would be that other segment, right? So then,
you're right. You're right.
like, can we find that segment with the law of cosines maybe? Because we know the angle and we know the two sides.
Yes, we could. I'm just trying to do things simpler. Just give me a sec. Well, so we can call this z plus dz. And just keep the, let's see if it works out. Z d theta. Yeah. Does this make sense, folks? If it does, then the rest is kind of straightforward. So this side is z plus dz, right? The new z. Okay? But then if you just cross multiply this, you get z plus dz. Hope that doesn't make you dizzy. Sine of negative d theta equal sine theta v dt. Are we good? No, not. Exactly, Leon. That's the whole point. So we know the angle is small, so we can replace it with just minus d theta as long as we keep theta in radians. And then we can actually neglect this contribution because it gives us a second order term. And it's not gonna matter when we like do the differentials. Is that idea clear? Happens in physics all the time. Because you want to write the time derivative. Time derivative is a limit of d theta dt, and this will just go to 0 in the limit because this is the dominant part and this is smaller part. Okay, So let me just rewrite it in a clean way. Z d theta equals negative sine theta v dt. There is probably an easy way to get this expression. But again, convince yourself that this is correct. Then from here, you can get d theta dt. D theta dt equals minus sine theta v over z. Okay? So these are differential equations, and in principle, physics stops here. Just do the math. And whatever your knowledge is about solving differential equations. So first off, it's a system of two differential equations. They're coupled, right? The z shows up in the theta equation and theta shows up in the z equation. So really, you have to solve them together. However, since we're really not interested in time, at least for the fox and rabbit variation of the problem, we're not interested in time, we can do a very silly trick. We can actually divide equation 1 by equation 2. Okay? And when we divide these derivatives, we get dz d theta. Does that make sense? What do we get on the right-hand side? We get v cos theta minus 1 minus sine theta z over v. Right? So we reduced the system of equations to just one equation. So technically, if you know how to solve it, you're good. And notice how this equation can be solved by a method called separation of variables. This is probably like method number 1 that everybody learns when talking about differential equations. Are you folks familiar with separation of variables? Those of you who were with me in the spring, I believe we discussed rocket equation, didn't we? Yeah, this is also done by separation of variables. The idea is that to rearrange the terms in the equation in a way that you have left-hand side dependent only on one variable and right-hand side dependent only on the other variable. And the two variables here are z and theta. So it's clear that you can actually divide everything by z and like divide everything by z and multiply by d theta. Then you will get dz over z equal, oh, v cancels, doesn't it? Yeah, v cancels. So you get negative cos theta plus 1 over sine theta d theta. Okay? Now technically you could just integrate both sides. 1 over z, the other one over theta, and that will give you some kind of answer, right? General solution to that differential equation. But you may probably be hesitant about integrating 1 over sine theta. So there is a nice trick for this particular combo. So let me put it somewhere on the side. Over here. So this actually not simplifies, it actually can be rewritten as sine theta divided by 1 minus cos theta. Look at it and tell me if it makes sense at all.
Yeah.
Actually, I just found that I need to fix this a little bit. I missed a minus sign, right? Because it was a minus, so it should be 1 minus cos. Okay. So really, we need the other way around, but it still works. Right? If you have minus here, it becomes a plus here. You see that? So if you just cross multiply, you kind of see that it's equivalent to the trig identity, sine squared plus cos squared equal 1. But this is a really neat trick because it allows us to do the integral simpler. So we have sine theta over 1 plus cos d theta. But this integral is very easy to do, right?
U equals cosine theta.
What's that?
Do you just do U sub?
You could, yeah. So what does it give us?
Like ln of 1 plus sine theta.
Okay, so on the left-hand side, we get ln of
1
z.
plus cosine.
Oh, and on the right, we have ln of 1 plus, is that right? Let's take the derivative of this. What do we get? Yes, thank you, Leon. Folks, what are we missing?
We're missing the negative because
Yeah.
yeah,
Yeah, when you take the derivative of the cos, you get a minus.
you got a negative sign.
Yeah, so you have to put a minus here, and plus a constant, of course, right? Let's not forget about the constant. It's actually very important here, especially when you're dealing with logs, because as you know, constant can be absorbed as a factor inside the log. So let's box this. This is almost it. We just need to carefully work with this answer. Let me just copy it on the next page. So we got ln of z equal minus ln of 1 plus cos theta. I don't really need to worry about absolute value because it's actually never negative, plus a constant. So how do we fix this constant? What do we do?
Can we multiply it inside of?
We can do all that, but just tell me how in general we approach fixing constants.
Oh, we set it to like some initial condition.
Exactly, we need to use the initial conditions. So folks, just reminding you, whenever you solve a differential equation, you get so-called general solution. In order to get the actual partial solution relevant for the problem, you need to use the initial conditions. This is a separate piece of data compared to the equation itself, right? And we have some specific initial conditions for the z, right? Because when theta is 90 degrees, z is equal to d, right? Okay, or h for the plane, right? But we're not doing the plane problem. So we're doing the fox and rabbit. So yes, exactly, Leon. So we put that in here, right? We get ln of d equal minus ln of 1 plus cosine of 90 is 0. Okay, plus the constant. So that fixes the constant for us, right? This is actually 0, right? This whole thing. So that means the constant is equal to ln of d. Too many letters, I agree. That's life. Okay, so now this goes back in here. And you see we can move this log to the left-hand side and combine with the z, right? We know that ln of z minus ln of d is actually ln of z over d. And that's a good thing because look, as a physicist, you should be really thoughtful about units. Whenever you see a log function or trig function, exponential function, the inside of that function must be what?
Positive.
Well, that's fine. In terms of units, what should be the units of the inside?
It should be unitless.
Exactly, it should always be unitless. So that means whenever you see things like this, ln of z, and z is kind of distance, you should be really concerned, right? So how come you can have a ln of meters? However, log is a special function because of this property. You shouldn't worry because there is always a constant you can absorb, and that will divide the z, and that can take care of units, okay? Because now we've combined this ln z with ln of d, and we got z over d. This is unitless. So just have that in mind. That helps you keep control on your differential equation. Okay, and then of course this is equal to minus ln of 1 plus cos theta. So now it's really easy to finish it off, right? So you just basically, how does the minus work with the logarithm? This is the same as ln of what?
One over.
Yeah, 1 over 1 plus cos theta. And then you can skip the logs, right? So you get z over d equal this, or z equal d over 1 plus cos theta. Folks, what kind of curve is this? You don't recognize it, do you? Oh, let me check the chat. Leon, yes, bingo. This is parabola in polar coordinates. Quick question, put a thumb up if you're familiar with polar coordinates and clap if you don't. Like use those reaction buttons. So Vincent and Alvin, you're familiar with polar coordinates and everybody else doesn't? Did they get that right? Yeah, so again, another side remark, and that may help us when we get to a topic that seems to be popular on F equals ma, Kepler's laws and everything related to Kepler's laws. So let me just remind you that if you have this equation, R equal d over 1 plus e cos theta, this is actually a second order curve, so to speak. E is eccentricity. Does that ring a bell? Again, if it doesn't, don't worry, we'll cover planetary motion in detail, but eccentricity is the feature of an ellipse. Well, if E is greater than 1, sorry, if it's less than 1, this is an ellipse. If it's equal 1, which is the case here, it's a parabola. If it's greater than 1, it's a hyperbola. If it's equal 0, it's a circle, right? If it's equal 0, R is just constant equal D, so this is just a circle. So this equation covers all like possible second order curves. But anyhow, yeah, this is a parabola. So what we really have done by solving for D is a function of theta. Oh, and by the way, now we can actually plug and check, right? We can say that theta final is equal to 0 degrees. That means cosine is equal to 1. So z final is equal to d over 2. Does that make sense? Yeah, so this part is easy. But now what have we done? We really have switched to the reference frame of the of the fox, because z is the distance of the rabbit with respect to the fox. So think of having solved this problem from Fox's point of view. So from Fox's point of view, the rabbit is actually going along a parabola. Isn't that interesting? So let me just quickly sketch what the fox thinks is happening. So let's sketch a parabola. So the fox is stationary in the fox's frame. The fox is sitting here and just keeps sitting here. The rabbit starts off here. Oh, and the fox is sitting in the focus of the parabola. Fox, focus. No pun intended. So this is the rabbit. It sits on the whatever you call it. So whatever is the line parallel to directrix passing through the focus. And then the rabbit goes to the top of the parabola. And as you may know, this distance is exactly twice as much as the focal distance. Does anybody know that fact about parabolas? It's
Yes.
easy. Yeah, okay, nice. Because if you think of like the regular parabola in the standard orientation, then that's kind of easy to see. So think about this, and get this parabola, and the focus is somewhere here. If this is y equals x squared, then where is the focus?
Well, you can use y.
Comma 1/4.
Yeah.
1/4, exactly. So this is 1/4, and that happens.
Game algorithm.
What's that?
Oh, nothing.
Platinum rectum. Some nasty Latin. Okay. So that happens at x equal 1 or plus or minus 1/2, right? So this is 1/2, and this is 1/4. So exactly half the distance. Okay. So I wonder what Andrew had in mind when he said he knew how to do it the hard way. So yeah, the rabbit is running along a parabola with respect to the fox. But like I said, you don't really need to know anything of this if you just use this nice trick. Okay. Any questions? Yeah, the directrix is the line that shows up in the definition of parabola. If you folks remember how parabola is defined geometrically, then that's where directrix comes into play. So directrix is a line here. It's here. So remember, like, I don't know, does anybody remember the actual definition of a parabola? So you need to specify a line. Yeah, it's about distance. Yeah, so you need to specify a line and a point called the focus of the parabola. So the line is called directrix. Then each point on the parabola has this property. It's equally distant from the focus and the directrix, right? Like this is halfway, it's obvious, but then if you move along this curve, you always have the same distance between the focus and the directrix. So in particular, this distance is the same as this distance. Again, I may have been sloppy drawing it, but the actual parabola would have that property. Yeah, I guess you learned something about parabolas today. And then this is focus of the parabola. Oh, and in that equation, in this equation, r is the distance from the focal point. As you may know, if you don't, again, we'll get to this and consider it in more detail. The sun is located at the focus of an ellipse, for example. So this distance is measured from the sun, from the focal point. Okay, on this happy note, let me make one last call for questions. Does anybody have any questions, comments, concerns? Okay, Alvin. So whoever are the other two people that are supposed to join us, please direct them to the Google Classroom website. Tell them that they need to do the homework. And again, tell them that if they can't do certain things,